right, so we're working with geometric probability. Anytime you're looking at probability, you have your successful outcomes divided by your total possible outcomes. So it's always a ratio of two things, which goes along with what we've been looking at with ratio of areas. So with our geometric probability, we might work with a dartboard and thinking about if each time we have another ring, we are increasing the radius by 1. Seeing as how I am bad at shooting darts, it's equally likely that I hit the dartboard as not, okay? So given that I hit the dartboard, what's the probability that I get a bullseye?
1.
It's not a 1. A 1 probability, by the way, means 100% chance. Right? It's not a 1/3. What you have to do is find the area of the center and then find the area of the whole dartboard. Now the area of that center circle is going to be its radius squared times pi, because area is pi r squared. So the area of the center is going to be 1 squared times pi, which is pi. The area of the whole dartboard is going to be 3 squared times pi. So my ratio is going to be 1 to 9, because it's going to be pi over 9. So the probability then that I hit the bullseye is going to equal 1/9. Can you see why a probability of 9 out of 9, which is a 1, a probability of 1 means I have a 100% chance, but a probability of 1 out of 9 means I have a 1 in 9 chance. Now, thinking about this, you can write a probability as a fraction, you can write it as a decimal, because it does not have to be stated as a ratio. So I could write this as a 0.11 chance, or a 0.1 chance rounding, okay? Or you can write it as a percent. 11%. I have about 11% chance of hitting the bullseye. So probability is kind of like what we've been doing, ratio of areas. But a probability you can state as a decimal, you can state as a fraction, you can state as a percent. So continuing on with another example. Let's say that we have a train that arrives at a station every 15 minutes. So train arrives, leaves, 15 minutes later comes back, leaves, 15 minutes later comes back. Okay? It waits at the station for 3 minutes. So 1, 2, 3 of the minutes is the train is there. Okay, so on. What's the probability that I arrive at a random time and the train is there? It is going to be 3 out of 15, which is 1 to 5. That's correct. So I have about 20% chance of arriving and the train being there, because 1 out of 5 is 0.2 or 20%. Okay? Now, what's the probability that I arrive when the train is not there, but I have no more than 5 minutes to wait? So I arrive when the train is not there, but I have no more than 5 minutes to wait.
1/3.
Well, first off, my successful would be 5 out of what? On arrival when the train is not there. How many minutes is the train not there? 12. So 5 out of 12 then, because only now it's just 12 possible outcomes. So I have 5 out of 12. I might leave it like that because I don't know exactly what decimal that is. I have a 5 out of 12 chance. A little less than 50%. 6 out of 12 is 50%. Right? Okay, so I have a 5 out of 12 chance. Now, let's do another one. We're at a carnival. And we have a table in front of us that's a bunch of lines that are forming squares. So this is what the table looks like in front of us. And imagine it as having perhaps more squares on there than I am drawing, because it's a larger table, right? And we get to throw a nickel onto this table. If the nickel touches a line, we lose. If a nickel does not touch the line, then we win. So this being our nickel, and that didn't work very well. That being our nickel, the question is, that's always interesting, isn't it? What is our chance of winning? Well, if we put the nickel on the table right there, we win, right? The fact is, anywhere clear over to here, that would be the farthest over it could be and still be a win. Let's make this a little more simple. We can really just focus on one square and one nickel. Did I get it yet?
I think it's good.
Okay. One nickel. Oh, Bandicam did not like that. Okay. So one square and one nickel. Now, I have to think, okay, well, right there would still be a win. And that's when the center of my nickel is right here. The center of my nickel could lie anywhere then, inside where? Well, anywhere inside, let's find the four corners of the square that the center of the nickel could lie in. Anywhere inside there would be a win if the center of my nickel lies there. Okay? Well, let's give ourselves some dimensions now. They tell me something about this nickel. They give us a dime instead of a nickel. Let's use their dime since they give us dimensions. I'm on page 462. They tell me that my square is 30 millimeters on a side. And that the dime has a radius of 9 millimeters. Now, the dime's radius of 9 millimeters is that distance right there. Radius of 9. So this distance here is 9. This distance here is 9. Right? Which means that this inside square is going to have what as its dimension?
12.
So 12 by 12 is what the inside square is going to have as its dimension. So now let's find our probability of win. We take 12 times 12, which is 144 square millimeters, divided by our total possible area of the square, which is 30 times 30, 900 square millimeters. And when we divide, use your calculator, come up with a decimal. What is our percent chance of winning? 16? So we have about 16% chance of winning. Tossing our nickel onto the table. Okay.
That's not good.
No.